let's start our, venture into the technical track. And the first speaker I would like to invite here on the stage is Jamie. Jamie, welcome on stage with a round of applause from everyone who's here. Jamie, the crowd is yours.
Thank you very much for the introduction. And welcome everybody here and everybody that is online as well. This afternoon, I'm going to talk about building highly available, secure infrastructure based on this new buzzword of zero trust. Before I dive into that, though, some people will probably think if you're going to be talking about high availability, then you're going to be using the number 2 a lot, because there is a kind of historical understanding that if you want HA, then just get another one, and if the first one goes wrong, then you've got the other one. Well, I'm going to try and avoid talking about the number 2 as much as I can, because one of the things about zero trust is it changes the way the world works. And so the way we implement HA in this new world is also going to be very different. So I'm going to take you on a journey looking a little bit about what zero trust is. Then we'll have a look at how it manifests itself, and we will see some of the tricks you can play to create a highly available infrastructure. First of all, I'd like to do a little bit of revision and just review our understanding of what zero trust actually means. It is a major trend and topic that is currently flavor of the month in the security industry. Arguably, it is a philosophy and a strategy that is going to change the way a lot of us put our infrastructure together in the coming years. And if we haven't started that journey, then a lot of people certainly are considering that they need to start that journey pretty immediately. Sadly, it is also a marketing buzzword. And there are plenty of organizations around who would produce anything and they will just tag it with zero trust to make you believe that it is based on the principles of zero trust. So sadly, you need to think about things like the hype cycle and where you might believe we've got to on that cycle at the moment. And yes, I think there were a lot of people who were trying to associate themselves with zero trust, possibly wrongly. Possibly that causes this peak of inflated expectations that everyone should be used to from Gartner's hype curve. But I'd like to think that we've got through that early phase now, and that if we're serious about IT security, then we should be serious about zero trust. And now we're starting to get enlightened as to what the benefits of zero trust can actually bring. So, a lot of people will ask the question, why should I be interested in zero trust? And what is it going to do for me? And it comes back to a problem that has existed for a very long time, and that is to do with a certain gap. That gap exists because we've all been using networks for as long as we can remember. Their real benefit is they make it super easy to connect. We come to a conference like this, we can just join the Wi-Fi network. It is very, very convenient. Sadly, in enterprises, we also have this requirement that we really want to restrict access to applications, particularly to critical applications, and that you should really be focusing on individual people and making decisions about whether they should have access to that application or that data or not. This creates the gap. We're using basically the wrong tool for controlling access to our critical infrastructure. The problem with letting the network do our application access control is that TCP/IP itself does not have a very good security model. It has always encouraged this really bad behavior, which is connect first and authenticate later. That means that typically all the resources are visible on any network that you have connected to. And only when you've actually got through to the target, the application or the data, do you then authenticate. And in this modern world, if you think about that, it just seems bizarre that we still operate that model in the current climate. The other problem with TCP/IP is it doesn't really have a policy language. It was never designed with that in mind. So if you ask the question, should a particular IP address have access to another IP address, then there is no way of actually deciding that apart from possibly just with a yes/no answer. So the big problem is that if we pursue this idea of using networks to control access, then we end up with wide open, flat networks, users frequently having access to hundreds, possibly thousands of resources if you work in a large corporation. And the network security teams basically give up on the idea of actually trying to control who has access to the network and rely on authentication when you actually hit the targets to define who should or should not get access. This is the reason why many networks have been hacked into in the past. And this is the reason why we've seen headlines time and time again. Once people break into a network and then exploit lateral movement to explore the network and find all sorts of interesting resources. It's that which Zero Trust is trying to address. This is a definition by NIST, which defines what Zero Trust means. It's a set of cybersecurity paradigms that move defenses from static, network-based perimeters to focus on the users, assets, and resources. Now, Zero Trust arguably was a phrase that was first coined by Forrester some years ago. And they pursued that idea fairly relentlessly for several years. And eventually it was picked up and has really become the backbone of the latest thinking in terms of the way we should be building our infrastructure. There are certain tenets that relate to Zero Trust, and you can see these really if you look anywhere, including Forrester, but NIST and others. And that is to ensure that all resources are accessed securely, regardless of the location of either the user or that target resource. That we should use least privilege at all times. And that we try and stay in control of our infrastructure. And we inspect what the infrastructure is doing on an ongoing basis, so that rather than waiting for something to fail or somebody to break in, we can maybe see things happening in real time, predict outcomes, and avoid bad outcomes by taking corrective action early. So what Zero Trust does is it compensates for the weaknesses I spoke about earlier. Zero Trust works backwards in terms of TCP/IP. So you authenticate first, then it will allow selective connectivity to authorized resources. That means that if the bad guys succeed maybe in getting through the authentication layer, they will still only see the original intended target that that user would have enjoyed. They will not be able to see your entire infrastructure. The other thing we need to address is the policy language. I've mentioned that already, that TCP/IP has a very weak policy language. And we really need to change that yes/no answer that we had previously to something more like a sort of "it depends" answer. And in theory, it should depend on almost anything you want it to depend on. And if the zero trust solution that you might be looking at can't answer a lot of these questions, then maybe it's not the right zero trust infrastructure for you. But we should be able to decide what our security policy asks us to check, and then simply implement rules that wrap around your security policy. Even down to interfacing with other systems, such as shown in the bottom right here, you could say, why should I let a third-party service engineer come into my network to access a system if there is no ticket open in the service desk system? So we shouldn't have open access. We should have access that is there when it is appropriate and only when it is appropriate. We've all heard stories about organizations being hacked into through things such as aircon systems or heating systems because you've left access to those systems open for engineers to provide ongoing maintenance and support. That is not zero trust. So NIST defined a relatively complex looking model for what zero trust should look like. It can be a bit scary, but somewhere in the middle here, you actually have the piece that does the work, whether it be control plane or whether it be the data plane down here. But the important thing is also to look at the associated systems that can interface in and out of your zero trust control plane. And these things that sit here on either side are the sort of things which can either feed into your zero trust system to make its decision-making capability richer, or can read in real time from your zero trust system to affect changes based on what it is seeing. Good example down the bottom here is SIEM systems, where you may well be able to set up alerts in here based on what this system is doing, and then those alerts in themselves could modify the behavior of this system. So you don't need to be working over the weekend when somebody is attacking your organization. You could actually use this type of approach so that it can defend itself over the weekend, and you come in on Monday to see what it's been up to. If we simplify that down to look at what the core might look like, you could end up with a policy decision point, a policy enforcement point. Obviously, you've got a user on the left, the subject, and they probably want to connect to a resource on the right-hand side here. And there is an implicit trust zone wrapped around that resource, which probably goes back as far as the policy enforcement point. And it's that implicit trust zone which you need to control access to. Right, now the CSA defined something called a software-defined perimeter, and this was done, I would say, almost in parallel from a time point of view with the concept of zero trust. But this SDP model that the CSA came up with actually represents a very good way of implementing zero trust in an organization. So zero trust isn't something you can go and buy as such. It's more of a concept, whereas the CSA's model for SDP is something, it's more real, if you like. It's something you could go and purchase if you wanted to. It looks pretty similar to the last diagram I just showed you. At the end of the day, you've got a policy decision point and a policy enforcement point. But typically, you'll all be used to this in your own organization. You have people, whether they're working at home or whether they're working in the office. Those people should be known to your organization, possibly through some kind of identity provider service, whether that be in the cloud, such as SAML, or maybe in your own organization. And these guys need access to some protected applications. So I'm going to use this model for the majority of the rest of this talk, so keep this model in mind. And so what I'd like to do is to move on, now we've finished our revision, and talk a little bit more about highly available zero trust. Now, as it says here, by its very nature, if you deploy zero trust properly, then it will be the backbone of your enterprise's connectivity model. It's the glue that holds your entire organization together. Now, you can think of zero trust as being like an application layer. It sits on top of your network layer. So we're not throwing away TCP/IP and its inherent problems. We accept the network as it is. We can probably simplify the network massively compared to how we have it today, because we're no longer trying to make the network do things it wasn't designed to do. So you can think of zero trust as being an application overlay that we're sitting on top of our network infrastructure. It provides the control plane, and the network itself can go back to doing what it was designed to do, which is connectivity. Now, because it's the glue and it holds everything together, HA is absolutely critical. And in the ZTP world here, it's much more important to approach it in a holistic way, rather than just saying, I need two of everything. So I'm going to take you on a journey looking at a number of tricks that we play at different points in our zero trust journey. And they're shown here on the screen. So we need to understand what single packet authorization is, how that works, how that enhances connectivity for users. We need to look at the policy decision points, the controllers, making sure that they are highly available. Ideally, it should be a token-based system which provides a great degree of tolerance. I've mentioned that it should work for everyone, so context awareness is critical. You don't want to give a third party the same access as your employees. It needs to adapt in real time, because the situation may change. It may change in your enterprise. Even the user situation may change. And you need to guarantee that users can always connect to what they need to connect to. So that's uptime. And finally, I'm going to take a look at monitoring, because if we don't monitor these systems in real time, they might as well not be considered as HA. So let's start by talking a little bit about single packet authorization. Now, this is based on the older idea of port knocking, which came from the Linux world. And the idea with port knocking is that a system would perform some kind of handshake with a target before it was allowed access. And port knocking in the old days just used to randomly knock on a number of different ports in a known order. And if you were a good guy, then you were allowed access. But if you were a bad guy, then access would be denied. Now, these days, we don't need to do this using port knocking. There are alternative approaches that you can take, because we have a lot of very good cryptographic tools around us these days. So it is those tools which we will use for things like SPA today. So the system I'm showing today uses SPA, and it's based on sending a specific signed encrypted blob of data, first of all. Now, the way we've done this is we have built it into both TCP and UDP. So you're allowed extensions in TCP, and so we have allocated an extension to ourselves, and the initial TCP handshake packet has an extension. It's an extra 94 bytes, and that contains this single packet that we send. Now, we use both TCP and UDP-based SPA. They are different, but they have distinct advantages. Now, TCP has the advantage of masking a TLS port. So if you have something like a Heartbleed vulnerability again, then it couldn't be exploited directly, because whilst you know that there is a TCP port available, you can't see it. UDP has the advantage of being able to completely mask the fact that you've got any TCP or TLS connectivity on your system at all. The trouble with UDP is it's not necessarily that easy to get UDP packets through in a reliable way. So what we have decided to do is to send 2 UDP packets always when a client wants to connect. We send one as an extension to the DTLS packet, which is much the same as an extension to the TLS packet. And we send a second one disguised as a DNS request using some weird encoded URL that you're trying to access. And we only require one of those 2 UDP packets to get through. And this works pretty nicely. Now, I have a system hiding behind here. The admin interface to the system uses standard TLS. And our standard port is on 8443 for doing administration. This would not normally be open to the internet. For doing administration, you'd usually have that hidden. But if we tried to do a curl to this, then you'll see with the typical response that you get when there is some kind of, in this case, NGINX service running in the background. So without any form of SPA, you immediately know what your target potentially is. Now, for normal access to our system, when we are not administrators and we're just users of, say, a client, then we would be connecting on 443 instead. Now, 443 is protected, and therefore, whilst you can see there is something there, you just get a connection was reset. So yes, there is a TCP connection there, but you don't know anything more than that at this time. Now, this system that's running here is not this one, it is this one. And in our global settings, we have check TCP and check UDP. And if I change the system to check UDP instead, that has now changed the status of all the gateways and all the controllers in the system. So they will now only accept connections using UDP. So if I now repeat what we just did here, then it's disappeared. Basically, what UDP has done is we closed the IP tables firewall rule for 443. And unless we receive a valid UDP packet, we do not open the 443 TCP port. When we do get a valid packet, we open it for a time window of 120 seconds, I think it is, to allow a TCP packet then to appear. If it does, we then maintain that connection. If not, as you can see, the system is now hidden. Now that is obviously a very good first step in creating a highly available system. Let's go back to where I was. It should be hiding here somewhere. What this gives us is uncontested connectivity. So we now have the good guys able to connect to our systems, whether they be the policy enforcement points or the policy decision points. And the bad guys typically may not even know that they exist. Next, stateless controllers. Now, it was very important that if you connect, you can connect to something. There's no point in just having NGINX running with nothing behind it. So, controllers obviously are hidden, as I've said, using single packet authorization. So the client will make a request initially to a policy decision point to say, do you know me? The controller will typically check credentials, possibly with a third-party IDP. And if it likes you, it'll give you back something in the form of a token to say, I like you. Now, stateless controllers have a huge advantage. Because they're stateless, they have no knowledge of you being connected to them. They're effectively performing a kind of REST service, and these clients are simply saying, please authenticate me, and the stateless controller gives you back a token to say, here you go. Job is over, connection is dropped. So that first controller now, you can see, is masked again with SPA. It's disappeared. Now, can controllers be truly stateless in an HA world? Not absolutely, but almost. There is hardly any information those controllers need to share between themselves, because all they've done is signed you in and given you a token. Any one of them could have done that. Yes, they might create an audit log to say you've been here, but beyond that, the only thing they did was assign you an IP address, a virtual IP address. So that IP address would need sharing with other controllers, but because those IP addresses are very, very sticky, the likelihood of your IP address changing in a properly set up system is close to zero. So there is almost no information to be shared. So the only other thing to do is you need to make it super easy to connect to these controllers. So what I thought I might do is just quickly download the log files from this client that signed in to one of these controllers just now. Those log files should be hiding in here. And if I look at the application itself that's signed in to that controller, then you see right at the top here, 2 lines of great interest. So that was resolving the controller, and you can see 3 IP addresses were returned. Key thing about HA is you don't want to do something clunky like put a load balancer in front of your policy decision points. Policy decision points. It in itself could fail. And because these things don't need load balancing, they just do a job that takes a couple of 100 milliseconds and they're done with you. It's much better to use DNS records and just return 3 IP addresses of the 3 controllers and let the system find one that's available, rather than putting another piece of redundant equipment in the way, and it in itself potentially becoming a failure mechanism. Oh, we've gone back to the beginning of that slide, so let's just whiz through that. So what that gives you is great level of service availability. Any controller can service you at any time, and there's no one in front of it to break down and cause problems. So let me just talk about use of tokens. Some systems probably don't use tokens, but tokens are a super powerful way of creating highly available infrastructure. Now, you've already seen that the controllers will pass a token to you. Well, that token is now passed on to your policy enforcement points, your gateways. And what that does is it tells the gateway that I'm legit and that, if you like, I'm going to allow you to connect to some application that I am protecting. So in this case, you can see that the gateways have read the token and they've passed a secure connection on to my application. Only the one application, I hasten to add, not all 3. Now, I'd like to just show you how powerful that is in action. So what I'll do is we will, let's see what I can find here that looks interesting, this guy. Now, I've got a simple system hiding here. Let's just see what's in our simple system. So we've got a controller and we've got a few gateways hiding in my system here. It's all hosted in Google at the current time, so you can see something a bit similar-ish hiding here in Google. So what I'm going to do is I'm going to select, I've got 3 gateways in the system. I'm going to select the 3 gateways, which are the policy enforcement points, if you like, and I'm going to put them to sleep just for now. So I'm going to suspend my 3 gateway instances. So they've kind of gone away. If I go back and look at my dashboard and I look at my appliance health, it'll take a while to load because it's polling those 3 gateways trying to get their health status currently, and it's going to struggle to get their health status because they're offline, as it says here. Now, I've got this client thing here that's kind of running. Now, I was logged into a collective, but I'm now going to log into the one I've just partially shut down, which is this one here. I'm going to log in as Annie, which is one of my test users. And so I'm signing into my controller, and my controller is still up at the current time. Oh, that's a shame. It's a demo. Let's just check here. No, it should be all right. It's the demo gremlins. You know how the demo gremlins go. Let's just try one more time. Nope, the demo gremlins are at work today. Ah, well. Anyway, what I was going to show you is that tokens, if you like, are sort of creatures that exist even without the system being fully functional. So effectively, once you've received tokens, and obviously from this other profile I have received tokens already, then those tokens can be consumed by gateways, even if the gateways weren't there at the same time as the controller was signing you in. But you will see a bit more of that later. So let me just bring those 3 gateways back up again. So they're all still checked, so I can just restart them. But effectively, the tokens that were passed to my client can be passed on to gateways, and they can be passed on to gateways at any point in time, as long as those tokens remain valid. And their validity is set by other parameters within the system. Now, let's go back to where we were in the presentation. Basically, the use of tokens gives you environmental immunity. So if your demos work, then effectively it means gateways can come and go, controllers can come and go, and as long as you have your tokens, then you are good. Now, context awareness is really important as well. It means that you can make decisions based on pretty much anything. It could be based on the time of day. It could be based on a particular process that is running on your machine. Pretty much anything should be able to set context. Now, because I've got this reluctant system that doesn't seem to want to let me sign in, I would have shown you what that means here. But instead, I will have to show you on another system. But basically, this means that you can adapt what is happening in real time. So typically, a connection will be established for you, the user. But what is important is that you end up with one solution that works for everyone. That means that your connectivity model needs to adapt to different communities. So if, for instance, you had a look at the way you set up access in these things, you could, for instance, have access control, as shown down here. And that access control is what would define, in part, the types of access that you would be granted. That also manifests itself in policies, where, for instance, if you were to look at this one here, you can see that it's checking for the device OS family being OS X. So you would have a particular community of users that need particular type of access. And if you wanted to change that, for instance, and instead your Windows users needed that kind of access, then you can change a particular parameter to Windows, and from then on, your Windows users would enjoy that type of access. So once you've got a rich language that you can use for defining your access, then it becomes quite easy to actually set up ubiquity, if you like, in terms of having policies to suit all your different user communities. Now, real-time access is something else that is important as well. So this user currently has access to application 2 only. The user tries to access another application, but at that moment in time, the firewall says, that packet you've just sent me, I can't pass that packet at this moment in time. The reason I can't is you don't meet some specific criteria that's set out. Now, this typically could be that the user at that moment in time is required to perform something like MFA. In theory, I can show you this at work. So if, for instance, we look at, say, this guy here, this is a product called UTrack. We use it for tracking tickets in our system. I could click on something and it will open magically. So I'm currently connected to UTrack through this client that you saw me connected with earlier. Now, yep, that's UTrack, but I might also, for instance, want to try and say ping UTrack as well. Now, pinging UTrack is not allowed, and as you can see, I'm not getting a request granted for ping, and it's popped up to say I need to provide additional authentication. So this is working in real time, and in this case it says please just re-authenticate with the existing provider that you signed in with in the first place. So that's similar to internet banking, where sometimes you're asked to provide your credentials again. And if we go look now, the firewall has now magically opened at that moment in time. And bingo, we have a system that allows you access. You can have various different forms of message, if you like, sent to the user. It can be as simple as this. Just please type in your password again. But there are also other, see what I've got hiding here. Actually, I think it's a shortcut over here. There are also other tricks you can play as well. So here, for instance, is a Windows desktop that you might want to connect to. And again, it's intercepted the traffic. It said that I need to use my security device on this occasion. That's kind of one of these guys. So you, in theory, can insert one of these guys, tap on your security key, and if I was to try again, this time it should actually launch and connect you to a remote Windows desktop. So this is the advantage of real time. And having real-time control provides a lot of benefit from a security point of view, because it means your security posture can become very, very adaptive. Let's go back to here again. Basically, it's very user-centric. So it's designed around the user. The user can self-help. The user can be given messages like, I'm afraid you're on the Wi-Fi network. You're only going to get access to that IP address from the wired network. Please move to the wired network. And then failover is another key thing. Yes, we're talking about HA, but one of the things that we've just seen, user connected to a gateway using the tokens that were provided by the policy decision point in the first place. But there is this big problem with designing HA gateways. If you've got firewalls in your organization, you'll know what it is. And that is that if you have two firewalls, there's one synchronization thing that has to happen between them. But if you've got three, there are now three synchronization things that have to happen. If you've got four, there are now six synchronization things that have to happen. Firewalls that talk to each other do not scale. You never see 4 or 5 firewalls in a cluster because they spend their entire time talking to each other rather than talking to users. However, in a token-based system, the user already has the tokens they need to connect to any gateway that's available on a site. It's a very small change to send a states token back from the firewall to the user. This is something that you can do optionally in this system. It's only a few K in size. So rather than trying to share states between appliances on a massive scale when you've got 5,000 users on a firewall, we simply pass a single state blob back to that user, and it's their states only that's passed back. When the gateway vanishes for whatever reason, that user now has the tokens they need and a states blob, and they can send that back and establish a connection to a new gateway immediately. The gateways have not passed a single byte of information between themselves. And then you can use auto-scaling to bring up another gateway. That becomes available immediately because that gateway has no requirement to synchronize with the previous gateways that were available. Indeed, it arrives, it has 0 firewall rules in it because it's waiting for a user to send them a token. Now, if we go look at this, it's still pinging away quite happily. If I was to look at the client here, then you can see a number of different sites I'm connected to where my gateways hang out. Oops. So I was using, for the ping service, I was using utrack. If I look at the shortcut details here and I look at the site, you can see that I'm connected to a particular gateway called got_purple1. So that's the current gateway I was connected to. So if I go to this system that's hiding here, I don't necessarily believe that message at the top of the screen, so we'll just refresh it. So if you look at this list down here, you'll find something, I guess, called got_purple1 somewhere. It gets easier when you sort it like this. Here's got_purple1. So this is the gateway, GW, that I'm connected to. And I will edit its configuration. Actually, that's not quite what I wanted to do. I was on the wrong screen. Just find got_purple1. Here we go. So this is got_purple1 here, and I am going to reboot it. So got_purple1 is now rebooted. And you can see there is a request timed out, and then we have continued. So what's happened there is it has just flipped to the other gateway using the token passing mechanism I was just explaining. So that's transparent failover and scaling, which is critical. Now, the last thing I just want to talk about is monitoring. People are in the habit of monitoring really boring things like CPU, RAM, disk, network. If you know what you're doing, it can be worth monitoring those. But when you need to understand how a zero trust system works, it's much better to recognize that, as you've seen, there can be a lot of autonomy in the way components work. It's very user-centric, so you need to think about what matters to users. And maybe you still need to monitor things like RAM. But you should really be thinking about three things in zero trust. You should make sure your infrastructure is working as you intended, that the functions within it are performing to the spec, and that you're not impinging on any physical limits. So for controllers, sign-in times, pretty critical thing for users. So why not measure sign-in times? It's much more useful than RAM usage. Your users couldn't care less how much RAM you're using, but they're super concerned with sign-in times. Gateways, okay, users want fast traffic, so yeah, network throughput could be a really good thing to measure. And there are some other things that you need to consider as well. Like a gateway handling 5,000 users might be making a lot of DNS requests or a lot of lookups to cloud APIs. Maybe you should be measuring those to make sure you're not hitting any quota limits. So before I summarize, I can just show you the sort of things that we might monitor in one of our collectives. Firstly, distribution of authorizations. I spoke about stateless controllers earlier. You might expect them to be a third each. So it's a super good trick just to check. They are, as you can see, about 1/3 each. Another interesting thing to check is this line here. This line here takes advantage of the fact that we have single packet authorization. We can therefore tell good packets from bad packets. So here, where we're using TCP, SPA in this system, I'm monitoring for unexpected TCP packets that we might be receiving. And you can see average sign-in times here for the 3 controllers, typically less than a second in this case. It may be interesting to look at failed authentications as well, because they could be bad guys trying to break in. But you must remember, with SPA on the front end, the bad guys don't necessarily get as far as trying to break in using some kind of bot. Now, the other thing I can show you is a typical gateway dashboard. You would expect to see similar things on a gateway. Again, you would expect to see a session split, but because I rebooted Purple 1 just a minute or two ago, it's hardly picked up any users since I rebooted it, and the majority of the users, 19 of them, are now on Purple 2 because I just rebooted it. Yes, you should be interested in NICs. Obviously, it's a gateway, but also firewall rules can be super interesting as well. Why are firewall rules interesting? Well, when you're doing everything at the user level, you're creating firewalls on a per user basis. So you can see here, typically we have in the region of 3 to 30,000 firewall rules active on a gateway at any one time. And that's because every firewall rule is written on a per user basis. There is no big rule, one for all. Everything is done at the user level. The other things that are interesting is sign-in time again. Why are you signing in? It's a gateway. The reason you're signing into a gateway is because of the use of tokens. So because a token has been sent to the gateway has to validate those tokens and ensure they're valid. Therefore, there is a sign-in process that has to happen. And the other thing, the final thing, if you like, that's of interest would be DNS. So on a gateway with 5,000 users, each user being treated individually, you can end up with a massive number of DNS requests. And therefore, from a high availability point of view, you want to make sure that you're not challenging your AWS cloud with API lookups or your DNS server with record lookups and making sure that you're not hitting some of artificial limit. So, in summary, really, Zero Trust is turning old thinking on its head, and therefore, in a similar way, our approach to HA shouldn't be our traditional approach. That needs to be consigned to history, and we need to think about it in a different way. HA is about providing ubiquitous, which means for everybody, unified, which means just one system, anytime access, which means basically for all hours of the day and night, with minimal management overhead because it looks after itself. So it's not just about the number 2 anymore. Thank you.
Thank you. Thank you. We have really just time for 1 or 2 questions. The first one will come from my side. So we are working at the network level currently, right? So the authentication will happen at the network level, and all the Zero Trust is implemented, just as I understood from your talk, just at the firewall or the central networking device. This is no agent deployed on the target system. This is where already the user or a computer or a system on the network is already authenticated and comes already to access the network, and then based on the authentication token, either access is granted or denied. Now, the core is, how do you get it working across multiple vendors, specifically if you have to work with multiple firewalls, let's say 2 different firewalls that have to synchronize, or there's no way that can be done and you have to have just a single developer or vendor firewalls to talk to each other?
Well, there's a couple of answers to that. I mean, the Cloud Security Alliance have tried to put together an SDP standard, I suppose you could call it, but it isn't really a standard. So it's a set of ideas. I would almost call it a sort of realization of ideas. And those ideas in themselves go some way to kind of establishing a standard. They, for instance, at one time were looking at SPA and seeing whether the types of extensions that you might want to add to TCP to turn it into an SPA type of packet could be standardized. But quite a lot of vendors went their own way and did their own thing, including us. So arguably, there isn't really a standard that you can use today for that purpose, but equally, ubiquitous use of a system should replace things like a lot of firewalls. They wouldn't have to work with network firewalls. Some people do keep network firewalls in place because they're very good for bulk connectivity, but when it comes to the user connectivity, it could be better to jump ships and choose an SPA vendor and work with them just for your user and device access.
All right. If there is any question from the audience, I would gladly take it from here. Where's my microphone guy? Okay, we've lost him. But for sure, do ask the question. I'll try to repeat it as well.
Actually, I have 2 questions, if you don't mind.
Well, let's go with one.
The policy for the user, can you do the policy regards to user posture? Was it clear?
Yeah, you mean device posture, I assume?
Yeah, device posture.
Yep. Well, because we have both agent and agent-less ways of connecting, if you have an agent-based way of connecting, then that agent is able to interrogate the local device and can pass back information about the device. The other way of doing it is because many organizations now have cloud-based services for device posture checking. So our policy decision point can make API calls to say, one of the vendors that support device security, and just say, for this device ID, could you please tell me the status of that device or some characteristics of that device? We would then consume that information and adapt our security posture based on the information we've received from somebody like CrowdStrike.
All right. All right, with this, Jamie, I thank you for coming over. And there's a small token from CERT.LV as well from my side.
Well, thank you very much for having me.
Thank you. Thank you so much.